I wanted to talk about why the critical value and the p-value of a t-test depend on the degrees of freedom of the curve. And this video will also help you with using the critical value table again. Maybe we've collected data from a group of 17 people for one sample t-test. And in a one sample t-test, the degrees of freedom is n minus 1, which would be 16. So this curve right here that our sample is a member of is a t-distribution curve with 16 degrees of freedom. Let me see if they have that in the table. Okay, 16 is fine. Maybe in another situation, we've collected data from 18 people for a one sample t-test, which means our combination of 18 people is a member of a curve or a set of combinations in which the curve outlining the t-scores is a t-distribution with 17 degrees of freedom. It's a t-distribution curve with 17 degrees of freedom. And the last one I'll do is a situation when we've collected data from 19 people. And the t-distribution curve that our sample is under is a t-distribution curve with 18 degrees of freedom. Now we can look up what our critical values are if we know the degrees of freedom. Let's start by looking up the two-tailed critical values. Remember, the two-tailed critical values are the critical values that have 2.5% in each tail. When you look up the two-tailed critical values, you have a negative critical value that has 2.5% of the possible samples to the left of it, and you have a positive critical value that has 2.5% of the possible samples to the right of it. So this area up here will also be 2.5%. Now we can find what these critical values are in this situation where we've collected data from 17 people. We go to our table. If we're doing a two-tailed test, meaning we're using the two-tailed critical values, we have to go to this row that says two tails and go to 0.05. And then once we have our column, we go down to the row that says 16 degrees of freedom, which is down here. And we have 0.05, two tails, and it meets up with this row of 16 degrees of freedom at 2.12, which means our positive critical value is 2.12, and our negative critical value is negative 2.12. Which means as long as our group of 17 people gives us a t-score that's at 2.12 or higher, or if it gives us a t-score of negative 2.12 or lower, or further to the left, we can reject the null hypothesis. As long as the t-score of our 17 people ends up in one of these two rejection areas, with a t-score either at 2.12 or higher, or at negative 2.12 or lower, we can reject the null hypothesis. If our sample ends up with a t-score in this middle area between negative 2.12 and 2.12, that's when we have to fail to reject the null hypothesis, because our outcome or our sample isn't in the rejection region. Now in this situation where we've collected data from 18 people, we can find out what the critical values would be in that study. We're still using 2 tails 0.05. This time we have 17 degrees of freedom, which means our critical values this time are actually 2.11 and negative 2.11. So since we collected data from 18 people and our curve has 17 degrees of freedom, that means that the value, the critical value that has 2.5% of the samples beyond it has changed. Now in this situation, 2.5% of the possible samples are at 2.11 or higher, and 2.5 of the possible samples are at negative 2.11 or lower. And why did this number change? It's because when the degrees of freedom of your t-curve or your t-distribution goes up, the shape of this curve outlining the possible samples changes. When the degrees of freedom go up, the curve starts to constrict toward the center and become less spread out. I mean, instead of being something like this, which is flatter and more spread out, it starts to become something more like this. It constricts and becomes taller and with thinner tails, like this. It's starting to become more bell-shaped with the higher degrees of freedom, and as it starts to become more bell-shaped, this value that has 2.5% beyond it starts to move in closer to the center, because here we have, with lower degrees of freedom, we have this thicker tail right here. But when the curve starts to constrict toward the center, suddenly the value that'll have 2.5% beyond it will be closer to the center, because with this thinner tail area, you have to go further to the center to find the point that'll have 2.5% in the tail. That's why the critical value changed from 2.12 to 2.11. As the curve is moving in toward being more of a bell shape, the critical value is moving in toward the center. And let's see what happens with this curve where it's a t-distribution curve with degrees of freedom of 18. Now our critical value is at 2.101. So our critical value isn't changing that much. It's just changing a little bit at a time as our degrees of freedom go up. Now we have 2.101 and negative 2.101. What if we suddenly increased our degrees of freedom massively? What would happen? Well, if we suddenly go up to 40 degrees of freedom, we get a critical value of 2.02, which is moving closer to the center. Let's go up even higher, 200 degrees of freedom. With 200 degrees of freedom, our critical values will be 1.97 and negative 1.97, which is somewhere around here and here. So it's still not moving in toward the center by a large amount, but it is moving in toward the center somewhat. So if we collected data from, let's see, from 201 people, our degrees of freedom would be 200, because 201 minus 1 is 200. So if we collected our data from 201 people, this would be the critical value we need to reach to reject the null hypothesis. It would be 1.972. So as you collect more data, the critical value that you need to reach to reject the null hypothesis becomes lower. It becomes closer to 0. That's part of the benefit of collecting more data, is once you've collected more data from a larger group of people, you don't have to reach such a high critical value anymore. The cutoff drops down to a lower number that's not as hard to reach. And now we've looked up the critical values for a two-tailed test, meaning all of these tails and all of these three curves are 2.5%. If we looked up the one-tailed critical values, we'd be looking at the critical values that have 5% at each end. And so those would be, in each of these, it would be a number somewhere here, around here, somewhere around here. So the one-tailed critical values are closer to the center than the two-tailed critical values, because they're the points that have 5% beyond them in the tail, in each tail. So they would be about here in this curve, and about here and here. And the one-tailed critical values also move in toward the center as the degrees of freedom go up. But in each case, with each type of curve that we're looking at here, the one-tailed critical value will always be closer to the center than the two-tailed critical values. So it's like both of these negative critical values right here are moving in toward the center, the one-tailed and two-tailed critical values. And these two-tailed and one-tailed critical values are also moving toward the center as our degrees of freedom goes up. But no matter how high your degrees of freedom is, the one-tailed critical values are always closer to the center than the two-tailed critical values are. Let's look at an example with 16 degrees of freedom. In this curve with 16 degrees of freedom, the one-tailed critical value, which is in this column, is 1.746. So it would be 1.746 and negative 1.746. Those are the one-tailed critical values for a left-tailed test or a right-tailed test. Let's see what the one-tailed critical values are for 18 degrees of freedom. They come out to 1.734. Which would mean that the negative critical value is negative 1.734. So if we look at the critical values up here, which are 1.746 and negative 1.746, and we go down here, we see that they've gone from this number down to 1.34 and negative 1.34. So as the degrees of freedom went up, these one-tailed critical values also moved in closer to the center, just like the two-tailed critical values did. And you can see that in each case, the one-tailed critical values are easier to reach than the two-tailed critical values are. If we collected data from these 17 people and we did a one-tailed test, we'd only have to reach 1.746. But in a two-tailed test, we'd have to reach 2.12. We'd have to be further, our outcome would have to be further in the tails to reject. So it's always easier to reject when you're doing a one-tailed test than a two-tailed test because your critical values aren't as strict. They're not as high of a number. That's the benefit of doing a one-tailed test when you can do a one-tailed test. But remember, in a one-tailed test, you have to commit yourself to using one critical value or the other one before the data is collected. You can't just wait until the data has been collected and then use either critical value. I talked about that in one of my other videos. Now, why does p-value depend on? We talked about why the critical value depends on degrees of freedom, but why would a p-value depend on degrees of freedom? When the degrees of freedom go up, the shape of your curve that outlines the possible samples changes, and it becomes more bell-shaped. So if you found the p-value is the percent of the samples that are beyond the t-score of your data set. So if we found a t-score of 2.1 and our degrees of freedom is low, which means we have this curve right here that it's flat and has these thick tails, our p-value is going to be all of this area beyond 2.1 in this thick tail right here. Or in a two-tailed test, it's going to be this area. It's going to also include this thick area below negative 2.1. So when the degrees of freedom are low and the curve is shorter and flatter like it is here, you have these thick tails that makes your p-value a higher value because you have a larger percent of samples beyond your t-score. But when the degrees of freedom are higher and the curve becomes more bell-shaped, the same test statistic or the same t-score won't have as many possible samples beyond it. The percent in this curve, the percent of samples beyond 2.1 won't be as high of a percent because this piece or this wedge that's beyond 2.1 isn't as big of a wedge anymore because the tail is thin. It's thinning out. The piece or the wedge beyond negative 2.1 also won't be as big anymore. So when you go from the low degrees of freedom to the high degrees of freedom, your p-value shrinks. And so with higher degrees of freedom, your critical value drops and becomes closer to 0, and your p-value also drops and becomes closer to 0. And let's see exactly what we mean by low degrees of freedom. I'm not sure what number to choose, but let's say we've collected data from 5 people in a one-sample t-test, which means the degrees of freedom of the curve is 4. So in this example, we've collected data from 5 people, and those 5 people have given us a t-score of 2.1. With this bell-shaped curve, maybe we have data from more than 30 people, maybe 40. And our degrees of freedom are 39. In order for the t-scores to have this bell shape, you have to have a higher sample size, which gives you a higher degrees of freedom. If we collect data from these 40 people and we get a t-score of 2.1, the p-value of this data set with 40 people will be a smaller p-value than the p-value you would get with these 5 people. So basically, if you collect data from 5 people and you get a t-score of 2.1, you'll get a larger p-value. And if you collect data from 40 people and get a t-score of 2.1, you'll have a smaller p-value. The p-value will be different even though the t-score is the same. So that's another benefit of collecting more data. When more data is collected and the sample size is larger, the same test statistic will give you a smaller p-value. And you want the p-value to be small because you want it to be 0.05 or lower. If I collected data from 100 people, my degrees of freedom would be 99, and the p-value would be even smaller. The p-value of 2.1 would be even smaller because the area of the curve beyond 2.1 would be an even smaller wedge. So the p-value in a t-test doesn't depend only on the t-score. It depends on the t-score and the degrees of freedom. Because it depends on the t-score because a higher t-score is further out in the curve, which means a higher t-score will have a smaller percent of samples beyond it. So a higher t-score will always have a smaller p-value. But the p-value also depends on degrees of freedom because when you take any certain t-score like 2.1, the percent that's going to be beyond it depends on the shape of the curve. And the shape of the curve depends on degrees of freedom.